Hello everybody, namaskar. So basically in this course advanced refrigeration system, I have included three refrigeration systems. One is the vapor compression system. So basically that is contains about the more than 50% coverage of the syllabus, and apart from that the ejector refrigeration system and the thermoelectric refrigeration system, those are there in the syllabus. So that's why that ejector refrigeration system and thermoelectric refrigeration system that I will discuss in details, but some other refrigeration system within that, some are basically some are widely used for some applications. So I think that I should give at least one or lecture for those refrigeration system which are not in the syllabus of this course, but those are used for the refrigeration application. So within that, one is the air refrigeration system or air refrigeration cycle. So that I will discuss or briefly discuss in this lecture. So first of all, let us see that what is the basic difference in between the vapor compression cycle and air refrigeration cycle. So both are basically the mechanical type cycle. So that means that both are using a compressor to compress the refrigerant from the heat ejection pressure to the heat addition pressure to the heat ejection pressure. So both are using a compressor. So that's why both are basically the mechanical refrigeration system. Or mechanical energy driven refrigeration system. So that's why it is very required or essential. So to discuss first what is the basic difference in between these two cycles. So for the vapor compression cycle, which we have already discussed, that the compression process is the and for all the cases we will see that the basic component, both cases basic component are also similar. So both cases we are using a compressor for the compression process, or compress the refrigerant from the low temperature, that heat addition temperature to the heat ejection temperature, and both the cases we are using some expansion devices to expand the fluid from the heat ejection pressure to the heat addition pressure. So for this case, only difference is that in case of vapor compression cycle, generally we will prefer the expansion devices as a expansion device, expansion devices, and in case of the non-work producing expansion devices in case of vapor compression cycle. But in case of Brayton cycle, reverse Brayton cycle, we will use the turbine as expansion devices. Then both the cases there is a heat addition process and heat rejection process, and we are using some heat exchangers for the heat addition and heat rejection. So that means if you see in this figure in a temperature entropy diagram, so the 1 dash, 2 dash, 3 dash and 4 dash, this is your vapor compression refrigeration cycle. So for this case you will see that the 1 dash to 2 dash, this process is the ideally isentropic process. So isentropic compression process, and also 1 to 2 dash for the reverse Brayton cycle. So the 1, 2, 3, 4, this is the reverse Brayton cycle or the air refrigeration cycle. So 1 dash and 2 dash and also the 1 to 2, both are basically the isentropic process, isentropic compression process. Then for the expansion, the 3 dash to 4 dash, this is the isenthalpic expansion, and the 3 to 4, that is the ideally isentropic expansion in a turbine. So that is for the air refrigeration cycle or reverse Brayton cycle. So then the 4 to 1, this is your heat addition process in case of the reverse Brayton cycle, and 4 dash to 1 dash, this is the heat rejection process for the vapor compression refrigeration cycle. Then the 2 dash to 3 dash, this is the heat rejection process for the vapor compression cycle, and 2 to 3, this is the heat rejection process for the reverse Brayton cycle. So the air radiation cycle is based on the reverse Brayton cycle or the Bell-Coleman cycle. So for the Bell-Coleman cycle also have the 4 processes, on to 2 the reversible compression or adiabatic compression process, 2 to 3 isobaric heat rejection process, and 3 to 4 this is also the adiabatic adiabatic expansion process in a turbine. Then 4 to 1 is the isobaric heat addition process. Okay. So the main difference in between these two cycles is that during the heat addition process and heat rejection process, in case of reverse Brayton cycle, there is no phase change. So that means the single phase heat addition process and single phase heat rejection process in case of a air radiation cycle. So that's why if you draw the TS diagram for both the cycle, then you will see that in case of vapor compression cycle, as the heat addition and heat rejection process can be isothermal process, so the cycle can be drawn by this way. But in case of reverse Brayton cycle, because those are constant pressure but non-isothermal heat addition heat rejection processes, so the 2 and 3 process we have to drawn by this way. So you will see that if you assume that the state point 1, that means the inlet of the compressor, and state point 3 inlet of the expansion devices, if you make both are same, okay, and based on that if you draw the cycle, then you will see that the point 2 temperature at point 2 that will be much higher in case of Brayton cycle. Similarly, the temperature at point 4 that will be the much lower for the Bell-Coleman cycle or reverse Brayton cycle. So that means the after the compression, that temperature should be always higher for the if you want to design the vapor compression cycle and air radiation cycle for the same source and sink. So the Bell-Coleman cycle compressor outlet temperature that will be much higher as compared to the vapor compression cycle. Similarly, the minimum temperature at point 4 that will be much lower as compared to the temperature at point 4 dash. So that's why the work input to the system for the given source and sink in case of Bell-Coleman cycle reverse Brayton cycle, that will be much higher, okay, much higher as compared to the vapor compression cycle. And that is basically happen due to the main reason is that in case of vapor compression cycle, that is the isothermal heat addition heat rejection. In case of Bell-Coleman cycle, heat addition heat rejection is not the isothermal. So due to this reason, you will see that the COP of the vapor compression cycle that is much higher as compared to the COP of the air radiation cycle or Bell-Coleman cycle. So maybe 2 to 3 times more COP we can get by using the vapor compression cycle for the same source and sink temperature. Okay, so that's why for the most of the applications or household application, all the systems are basically based on the vapor compression cycle, not the air radiation cycle. Okay. So, and another thing related to the air radiation cycle is that cycle is maybe the open type or maybe the closed type system. So, open type of system, that means for this case after the inlet condition of the compressor, that is just a atmospheric air or the normal air. So that side is open, inlet is open, so we can that can directly get from the outside air or atmospheric air. Similarly, the outside of the turbine outlet condition, that is also open to the space where we need the cooling effect. So that means the air is used as a refrigerant for this system. So air can be directly taken from the atmospheric air, and that is reacted to the space where we need the cooling. But in case of closed system, the air is recirculated. Okay. So in case of closed system, when the air is recirculated, so this system is just like a vapor compression system, vapor compression cycle. So vapor compression cycle is also a closed cycle. So for that case, the COP, if you compare in terms of COP, so vapor compression system has the much higher COP as compared to the closed Brayton cycle. But some cases, as the air is a working fluid for the Bell-Coleman cycle or air refrigeration cycle, so open type of cycle is widely used for some applications like the air conditioning system. We can use the open type of Bell-Coleman cycle or reverse Brayton cycle. So if you see the cycle for the simple air refrigeration cycle, so we will see that this also contain the 4 component. So one is the compressor, 1 to 2, this is the compression process in a compressor, and this process may be the adiabatic process or maybe the non-adiabatic process, but ideally we will assume this is the adiabatic compression 1 to 2. So that means this may be isentropic process or non-isentropic process. Similarly, in case of turbine 3 to 4, this is the expansion process. So theoretically we will assume the adiabatic expansion process from 3 to 4, and that expansion process may be the isentropic or may be the non-isentropic with the given isentropic efficiency of the turbine. And the process 2 to 3, this is the heat rejection process. So this heat is rejected to the ambient or any other heat sink. Okay, any heat sink. And similarly, the heat exchanger at a lower side, that means the process 4 to 1, this is the heat addition process, and here there is a heat addition from the heat source. So now for this case working, which I have already told that the process 1 to 2 is adiabatic compression process. So for this case, the pressure will be changed from the P1 to P2, and the temperature will change from T1 to T2. So the P2 by P1, that is basically the pressure ratio for this compressor, and ideally we may assume the isentropic process, but for the theoretical analysis, actual process may be the non-isentropic adiabatic process with the given isentropic efficiency of the compressor. Similarly, for the heat rejection process, this is the isobaric process, constant pressure process, and temperature changes from T2 to T3, and again the expansion process, that we will assume as adiabatic expansion process, and ideally that may be isentropic, or we can use the non-isentropic but adiabatic expansion with some given isentropic efficiency of the turbine. Then temperature for this case decrease from 3 to 4, T3 to T4, and then there is again the heat addition process 4 to 1. So during this process, basically heat is absorbed from the heat source, and the temperature will change from the T4 to T1. Okay, so this cycle we can represent in a pressure volume diagram and also the temperature entropy diagram. So for this case, ideally we can assume that the compression process 1 to 2 is isentropic compression, 2 to 3 is the isobaric heat reaction process, then 3 to 4 is again isentropic expansion process, then 4 to 1 is again the isobaric heat addition process. So this also we can draw in a temperature entropy diagram. So similarly 1 to 2 and 3 to 4, these are the isentropic process, and the 4 to 1 and 2 to 3 both are the isobaric process. Okay, so for the performance evaluation of theoretical calculation, the specific cooling capacity we can write in form of the Cp into T1 minus T4. then we can evaluate the specific compressor work, that is the Cp into T2 minus T1. So and the specific turbine work, that will be the Cp into T3 minus T4. So that means the net specific work input to the system, that will be Cp into, that means the compressor work minus turbine work, Cp into T2 minus T3 minus Cp into T1 minus T4, and this also sometimes written in term of the heat rejection minus heat addition. So from the energy balance, the heat addition minus heat rejection minus heat addition, that should be equal to the compressor work minus turbine work. So the net specific work input we can write by using this equation. So ultimately the COP of the system, that is the cooling capacity by the net work input. So cooling capacity, that is Cp into T1 minus T4 by the heat net work input, that is Cp into T2 minus T3 minus Cp into T1 minus T4. So if you rearrange all the terms, so first of all Cp will be cancelled out, and if you take the common T4 in the numerator, so that will be T1 by T4 minus 1, and lower side the T3 into T2 minus T2 by T3 minus 1, and that is again T4 into T1 minus T4 minus 1. Now the pressure ratio of the cycle, that is the Rp, that is equal to P2 by P1, and that also equal to P3 by P4. Okay, now if we use the isentropic process formula for the process 1 to 2 and 3 to 4, then we can see that if you write the equations which is relation in between the temperature and pressure, so we can write T2 by T1, this is equal to P2 by P1 to the power gamma minus 1 by gamma. So this is the reversible adiabatic formula for the reversible adiabatic process or isentropic process 1 to 2. So that means the T2 by T1, that is equal to basically the P2 by P1, that means the pressure ratio to the power gamma minus 1. Similarly, if you consider the process 3 to 4, that is also isentropic process. So for this case also we can write T3 by T4, that is equal to P3 by P4 to the power gamma minus 1 by gamma. Now P3 by P4, that is equal to P2 by P1. Okay, that means this will give that the T2 by T1, that is equal to T3 by T4, and that also we can write that the T2 by T3, that is equal to T1 minus T4. So in the equation for the COP, that the, if you recall that equation, this one, so the T1 by T4, that is equal to T2 by T3, so that means the T1 by T4 minus 1 and lower side T2 by T3 minus 1 and T1 by T4 minus 1, that will be cancelled out. So that means the COP of the system, that can be written by the T4 by T3 minus T4. Okay, so that we can write by this way, T4 by T3 minus T4, and this also we can write 1 by T3 by T4 minus 1, and T3 by T4, that is basically equal to the pressure ratio Rp to the power gamma minus 1 by gamma. So that will be ultimately we can write that the 1 by Rp to the power gamma minus 1 by gamma minus 1. So that means the finally you can see that the COP of the reverse Brayton cycle can be written in term of only the pressure ratio. Okay, so only the pressure ratio in the in case of the isentropic expansion and isentropic compression. Okay, but if we assume that for the cycle the expansion and compression process are not isentropic, so for that case there is some isentropic efficiency of the compressor and isentropic efficiency of the turbine. So for that case also we can establish that the COP can be written in term of the pressure ratio and the isentropic efficiency of the compressor and isentropic efficiency of the turbine. Okay, so that means for the ideal condition, the COP is only depending on the pressure ratio. Either pressure ratio will change, then your COP will also change. So if you see this table, that how the COP of a reverse Brayton cycle or Bell-Kahneman cycle, that will change with respect to the pressure ratio. Okay. So if the pressure ratio is equal to 1, so if you use the above equation, so basically the 1 to the power something, so that is also 1, so 1 by 1 minus 1, that will give infinity. So that means for the pressure ratio 1, the COP is infinite, but for the pressure ratio 1, that is practically not feasible. Okay. So if you take the pressure ratio 2, then the COP will be 4.56. If the pressure ratio 3, then COP will be 2.7 on. Then if the pressure ratio 4, this will be 2.05. Pressure ratio 5, 1.73. So by this way, the COP of the reverse Brayton cycle or the air efficient cycle, that is depending on the pressure ratio for the compressor. Okay, so apart from, another issue is related to the actual cycle for the vapor compression cycle. So in the lower diagram, the actual that air efficient cycle, that is also given in this figure. So for the actual case, we can see that on to 2 so this process is basically the maybe non-adiabatic process, and also the so this is non-isentropic process. Similarly, the 3-4, this is ideal isentropic, but the actually non-isentropic. So 3 to 4 this is the non-isentropic expansion process. Similarly, the 4 to 1, we have although assumed that the heat addition process is isobaric, but the actual heat addition process is not isobaric. There is a pressure decrease of pressure or pressure drop during the heat addition process. So that pressure drop from the P4 to P1. Similarly, for the heat ejection process, during that process also there is a pressure drop. So that means that is not isobaric process. So 2 to 3, this is the actual heat ejection process where the pressure is continuously decreasing, or there is a pressure drop during this process. Okay, so there are some advantages and disadvantages which are related to the air efficient cycle. So the design is very simple and lightweight, this is, so that's why this is very good for the aircraft application. So there is no phase change, that means the air remain in a gaseous phase, so that we can directly use the air for the cooling purpose. But there are a lot of disadvantages for this cycle. So the main disadvantage is the lower COP. So heat transfer so the COP of this system, that is very low, or that is lower as compared to the vapor compression system. So that as compared to the vapor compression system, the size of the component, that is bulky, because I have already told in some lecture that the component size, that is depending on the specific volume of the refrigerant or working fluid in that component. So the in case of air, that is always in a vapor phase or the gaseous phase. So that means the air density is very low as compared to the liquid the density of the refrigerant for the vapor compression system. Okay, so that's why for the vapor compression system the density is higher, so that's why the component size is lowered, but the air refrigeration system density is lower, that's why the component size is higher. So that means the density of the refrigerant, that is also a very good influential parameter to decide the size of the component of the system. Okay, so in case of air refrigeration cycle, the component are much more bulky as compared to the similar component in the vapor compression system. Okay. So inefficient at the low speed, so this will work better in case of higher speed. Okay, but at the lower speed the performance is not so good. Okay, so these are the some reason, that's why the air refrigeration cycle is only limited to the aircraft application, but for the household applications the use of the reverse Brayton cycle, this is basically that is not in a practical use. So maybe some prototype or some specific device has been made based on the reverse Brayton cycle, but in general for the household application or industrial applications or any type of stationary applications or mobile applications, that like a car, train. Okay, so for these applications the air refrigeration cycle is not used in general. Okay, so although there are some specific application we can see for the air refrigeration cycle. So one application is the aircraft cooling system. So for the aircraft cooling system we can use this refrigeration system. So why the air refrigeration system is preferred in case of the aircraft cooling applications? So main reason is that in case of aircraft refrigeration system we have also, or that means the aircraft refrigeration system, we have also maintained the ambient pressure in the cabin. Okay, so that's why the in case of aircraft system that if you use the air as a refrigerant, so that air after the expansion, that air we can directly inject to the cabin, so that that will basically make up the leakage from the any air leakage from the cabin, and that will help to maintain some constant pressure inside the cabin. So that is the main reason why are using the Brayton cycle, reverse Brayton cycle for the air conditioning application of the aircraft. And another reason is that this air refrigeration cycle we can easily integrate with the air Brayton cycle. Okay, so Brayton cycle is generally used for the power generation in a aircraft. So the air refrigeration cycle can be easily integrated with the air power Brayton cycle. So these are the some reason why the aircraft refrigeration system or why the air refrigeration system is used in the aircraft application. And apart from this, the gas liquefaction plant we can use the air refrigeration cycle, and also some military application and also the space application will prefer the reverse Brayton cycle or air refrigeration cycle. Okay, so these are the some specific applications of the air refrigeration cycle. Thank you.